Hi, we are Ricardo and Sania, and we're going to present X-ray fluorescence.
The objective of this experiment was to study the fluorescence spectrum of different materials, and the specific goals were to verify the elements present in different samples through their spectrum. We are going to begin with the introduction. In 1913, the physicist Niels Bohr published a complete atomic model with a functional configuration of electrons, and among these models, he also published a series of postulates. The first postulate says that an electron in an atom moves in a circular orbit around the nucleus under the influence of Coulomb force, and this movement follows the laws of classical mechanics. The second one tells us that an electron can only move in an orbit for which its angular momentum is an integer multiple of Planck's constant divided by 2 pi. The third one says that even though the electron is in constant acceleration when it's moving in the allowed orbits, it does not radiate electromagnetic energy. But the fourth postulate says that electromagnetic radiation is emitted when an electron that initially moves in an orbit with certain energy changes to another orbit of another total energy, and the frequency of this radiation will be equal to the change of total energy divided by Planck constant.
The fourth postulate shows how the frequency emitted varies according to the quantization, as it depends on the energy of each orbit, as it can be seen in equation 1, where that h with the bar is Planck's constant. When the X-ray interacts with an atom, the electrons in the interior layers are rejected. So to return to the unstable configuration, electrons in the outer layer releases energy, and this process is known as fluorescence. The spectrum obtained from the X-ray fluorescence has characteristic lines in specific positions, which varies depending on the element analyzed. The material used for this experiment are the X-ray apparatus with a MO X-ray tube, an X-ray apparatus with a CU X-ray tube, a ionometer, an X-ray energy detector, an alloy target set, a CASI sensor, an MCA box, an HF cable. The tabletop was connected and the high voltage tube was set to 35 kilovolts. The emission current was set to 1 milliampere, and then the high voltage was switched on and starting recording the spectra for the targets in the alloy tube for the MO and CU. We obtained the fluorescence spectrum for 4 different target sets and X-ray produced by the MO tube. As it can be seen in figure 1, we can see that it has 2 peaks, one in around 7.2 and one around 8.7. For target 2, it also has 2 peaks. One can be seen around 10.5 and the other around 11.5. Also for target 3, we have 2 peaks, one for 10.5 and one for 11.2. For target 4, we have many peaks, but there is a peak that is more visible, is around 9. Subsequently, the energy spectrum graphs for the same 4 targets, but using the CU tube. For target 1, we also have 2 peaks, one around 8.5 and one around 7.1 kilo electrovolts. For target 2, we have 1 peak and 1 semi-peak. The peak is around 10.5 and the other real peak is around 11.2. For the target tree, we also have two peaks. One is around 10.5 and the other around 11.2. And for target 4, we also have many peaks, but one that is more visible and is around 9. Finally, we compare the results for the spectrum graphs in the literature.
Well, here we can see the fluorescent spectrum of target 1. This one was given by the literature, and we can see that the graph obtained using the Mo cube and the Cu cube are similar to this graph. However, the characteristic lines differ in energy value a little bit, because here we can see that the highest peak is around 6.5, while our peaks were around 8.5. For target 2, we can see a similar relation. We observe that our spectrum graphs obtained are similar to the one given by the literature, but we also have slightly different in energies. For the third target, we observe the same behavior. We can observe that we have similar peaks. However, the highest peak that the literature gives us is around 8 kiloelectrovolts, while our highest peak is around 11 kiloelectrovolts. And finally, for the fourth target, we observe again the same relation. Here we can see that the peak is around 6, more or less, 7 kiloelectrovolts, while our peak is around 9 kiloelectrovolts. So we observed that even though the graphs obtained share certain similitude with the ones from the literature, the values of energy at which the peaks are differ slightly. We know that the targets were made of different alloys. Here in this table, we present the different mixtures of elements that had each target. Using the spectrum, it is possible to, as we said in the introduction, it is possible to obtain the elements that compose each target. However, we saw that the spectrum that we obtained differs slightly in the energy values of the peaks from the ones that the literature gave us. And even though this difference is small, it is of great importance, because completely different elements may have characteristic lines at energy values that roughly differ. So we believe that the discrepancy with the literature was due to the values of energy provided, and maybe using the CASI program, we will have better results.
We obtained the spectrum produced by the X-ray fluorescence for different samples. We tried to determine the elements that compose each sample by comparing the elements and the figures with the graph provided by the literature. It was observed that the different spectrum obtained had a slightly deviation to the right in comparison with the literature. And here are our references. Okay, thanks.
Thank you.